Exams will be returned on Wednesday. Okay. I left you with the region on the right here, but the statement I'm about to make applies to both of these. Neither of these are nice as type 1 or type 2 regions. The left one's a circle of radius 2. What's the equation for a circle of radius 2 centered at the origin? Almost. Not root 2. It's 2 squared. And if I wanted to do this as a type 1 region, I'd have to write this as y equals. So if I did this as type 1, it would be negative root 4 minus x squared less than or equal to y less than or equal to positive root 4 minus x squared. And then x would go from -2 to 2. And that's just disgusting. Because when I integrate with respect to y, I'm going to have to plug those things in for y. Blech. Disgusting. Same problem exists in the region on the right, which is the one I left us with on Friday, because now I have two different semicircles. The upper semicircle has radius 2. The inner semicircle has radius 1. But if I try and do this as a type 1 region, technically, it's 3 type 1 regions. It's the region between the top circle and the x-axis between -2 and -1. It's the region between the top circle and the bottom circle between -1 and +1. And then it's the region between the top circle and the x-axis between 1 and 2, which means I'm going to have 3 different sets of limits of integration. Pardon my bluntness. Hell no. I don't want to do that. It's unreasonable to do that. I grew up in Florida. The Southern comes out every now and then. How do I get around this? I don't want to do this as type 1. By the way, if I tried to do it as type 2, it would be just as bad, because as a type 2 region, I'd have to divide it horizontally. Then I'd be going from the right x to the left x, but then I'd have 2 different pieces here. No, 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 just no. Chapter 10. Way back in Calc 2 in chapter 10, we decided that some curves were easier to do if we didn't do them in x and y. What did we do instead? Aha. In polar coordinates, how can we describe each of these regions? Let's think about the circle over there on the left. Polar coordinates are r and theta. So now I think about the way I'm slicing this up differently. Instead of slicing, first making a little box, moving it up and down, that's dy, and then moving that strip of boxes to the left and right, that's dx. Instead of doing the strip of boxes in that rectangular orientation, I want to build my strip of boxes in these variables. That means I go out from the origin in terms of radius, and I think about going around in terms of angle. So think of it like you're unfolding a fan. First, I have to decide where the radius is, then I have to decide what angles I'm covering. If I start at the origin, my radius would go from where to where? In this circle. But now, what angles do I cover? Okay, but I got to start somewhere, right? I need to cover an angle total of 2 pi to go all the way around. So I could say, oh, well, let's go from 0 to 2 pi. I could also just as easily say we're going to go from minus pi to plus pi, right? Or from pi over 2 to 5 pi over 2 to get all the way around the circle once. You don't have to have this particular set of angles, but this setup describes the circle. Guess what? That's not a type 1 region. That's not a type 2 region. That's a rectangle. Number, 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 number. Just my coordinates aren't X and Y. I'm going to say that again because it sounds really freaking stupid. That circle is a polar rectangle because its boundaries are only constants. How about the arch on the right? I could describe this region in polar coordinates as well. Smallest radius in that arch is 1, biggest radius is 2. And I'm only going on a half circle. And I always figure out whether I'm going to start in the direction of theta. I would go from 0 to pi as I go around in a positively oriented angle. That's bounded by nothing but numbers. That's a rectangle also. If my region is easier to describe in polar coordinates, then it might make sense to shift everything to polar coordinates. Now, the problem is twofold. First of all, I have to change the description of my region. But then I have to change my integrand. I have to change my function. I have to change my dA. All right, wait a minute. Wait a minute. Now I have a problem. When we did an integral dx dy, we made a little piece of area by taking a box dx and a box dy, multiplying those together, because a rectangle is length times height. But now I'm not looking at pieces that are boxes left and right. I'm looking that are pieces that are dr and d theta. dr goes out, d theta goes side to side. Take a look at my problem. This is a piece of polar graph paper. This particular piece of paper is older than I am. What happens as r gets bigger? For the same change in theta, the box gets bigger. Just look at this inner ring here. That's 0. That's 5 degrees. This box and this box and this box all have the same change in r and the same change in theta. But this box is clearly smaller than this box. And when I get out here, instead of just using one box, they double them up. But notice they still keep getting bigger. This line at 10 degrees versus this line at 0 degrees. That's the same size ring, both in height and width, angularly, as this is. But that is only 4 boxes, and that's a crap ton more boxes, isn't it? So I have to account for this difference when I think of dA. dA is going to change. It's not just dr d theta. Now, I often get asked, where's that extra r come from? And the easiest way to think of it is to look at the picture on page 1011, which is a grossly blown up version of the picture I was just using. So they have this. Here's a left bound and right bound in theta, an upper bound and a lower bound in r. I'm going from A to B and from theta 1 to theta 2. Well, A and B there, alpha and beta. This little box that's shaded in kind of an orange color would be one of my little sample rectangles. But how far apart those two lines get as we go out depends on how far out we are. So I need to actually multiply by the actual value of the r's there. I pick my sample point. I average the two r's. The further out we get, the wider that box is going to get. And that's where this extra value of r comes from. Now, there's actually another way to derive this r by thinking of this as a nonlinear transformation. And then we can think about changing this element as based on that transformation. We'll do that later in the chapter. That's the result of a gentleman by the name of Jacob. It's his last name, Jacobs. So we'll talk about that later on. But that means if I want to change some integral from x and y to r and theta, I not only have to switch the description of my region to polar coordinates, I have to switch the integrand. Wait a minute. I have to change x and y to r and theta. I have a formula for that. What changes from x and y to r and theta? And then for dA, I get that extra r. Now, sometimes that extra r is a godsend. And sometimes it's just more of a pain in the butt. But it's there and we can't forget it. If you're not happy with where it comes from, I understand that. I promise to make it more clear later in this chapter. Gesundheit. Shall we try one? Now, different textbooks have different notation. Oh, wrong button. Have different notations here. We're often using the inside of a circle. If I'm going to use the inside of a circle, I will often call it the disk centered at A of radius R. And A is going to be a point, right? So that'll be the X coordinate, Y coordinate. In our case, it's the origin. So this circle, the upper half of the circle, I could write this as the upper half of D origin 3. That notation really comes from complex variables. More on that if you take that next semester. But I like using it. I've used it in some of my notes. I didn't want to write it down and not explain to you what the hell it is. How do I rewrite that integral? Changing everything to polar. Wait, before I do that, should I change all this stuff to polar? Well, think about your region. In polar coordinates, a half a circle is a polar rectangle. I go from radius to radius, from angle to angle. And they're all numbers. My region looks like that. Again, understanding that I'm a crap artist. What's a polar description of that half circle?
Was cosine squared.
That was the function in the problem in the textbook. That's our f of xy. Right? That was the problem that they asked me to integrate. This is just a description of R. This is just a description of the region. I haven't described the function. The function will be some surface above that, right? So I'll get some cosine, and cosine should go wiggle from the top down, right? And it'll go from 0 to 3. So somehow there should be a wiggle living above that half circle. And I want the volume inside the wiggle, under it. Better? Okay. Right. I'll make this R. There. What's the description of that region in polar coordinates? Jack? Well, but I need boundaries that are, like that. I like using pi, I like using 3, but what are the other sides?
It's negative 3, 3.
It's a radius, right? That's a radius. If I start over here, that's already at a radius from the origin, right? So if I'm going DR, I'm going from inside to outside. What's the inside level? The inside?
Sorry, 0.
And the outside will be 3. Now you said pi. That's over here. What?
0.
Because I'm going from there to there. You see the fan unfolding? Okay. Let's change this entire double integral from x and y into polar. Which means I need to convert x to r cosine theta and y to r sine theta. But I get to be sneaky about that. What are the other change of coordinates when we start in r theta and go back to x and y? This is when you open your textbooks back to chapter 10 and go, I don't remember, let me go look. There's an x squared plus y squared, and you just said r squared equals, hey, lo and behold, that makes this the double integral of the cosine of r squared. Now I need dA. What's dA? And now, since I wrote dr on the inside and d theta on the outside, the r limits go on the inside, and the theta limits go on the outside. Because still at heart, I am a little kid. In my head, every time I hear it, r and theta. It's pirate coordinates. Been making that joke for 30 years. It's not going away anytime soon.
If you do substitute, x equals r cos theta or y equals cosine theta, you would still get the r squared, you just take one.
Because I get r squared cosine squared theta and r squared sine squared theta, and I factor out the r squared and then cosine squared plus sine squared, which is 1, it gives me r squared times 1. But I like being able to do it in one fell swoop, because here it is, the bottom of page 600, oh, careful, bottom of page 659, I have the original change of coordinate equations, x equals r. But at the top of the very next page, if I can turn one freaking page, people, I have r squared equals x squared plus y squared. But now you see why I am very happy to have that extra r in my GA. That extra r allows me to do that integral. Otherwise, I'd have cosine of r squared and no r on the outside. I wouldn't be able to do, oh crap, I'd have to use some sort of trig function identity to make that work. But with the extra r, that's a u substitution. But wait, it's even better. This is a rectangle. In r and theta, those are all numbers. This is a polar rectangle. And that means I can reach to my back pocket and say, Fubini theorem. The corollary to Fubini's theorem says that if you have a rectangle and you've got a function of one variable and a function of the other variable, you can separate the two integrals. This is actually not a double integral. This is the product of two single integrals. Because I can think of this as a function of just r and another one of just theta. And those two integrals are easy. The one on the left is trivial, and the one on the right is a U sub. I'm missing the two, so I'm going to go 1/2 in front of that. So I get here, I get the integral from 0 to pi of 1 d theta. And over here, I get the integral of 1/2 cosine u du going from 0 to 9 because I changed the limits with my u substitution. You don't have to. You could leave those as r limits, then you just have to switch back when you were done with the integral. The integral of 1. Ta-da. Theta, evaluated from 0 to pi. The integral of cosine. But the 1/2 stays there, so I get 1/2 sine u from 0 to 9. If you left them as 0 and 3, you'd have 1/2 sine of r squared, which would give you the same result. So here I get pi minus 0, and here I get 1/2 of sine of 9, whatever the hell that is, minus 1/2 sine of 0. What's sine of 0? Yay! I don't even have to write it down. If you want, you can give me a decimal. I don't know what that number is, but that's good enough. Questions? Because I am now doing integrals with trig functions involved, I'm going to have to dig back to chapter 7, the beginning of Calc 2, chapter 7, section 2, where we did all of those cosine to some power, sine to some power problems. Because if I had r squared and, I'm sorry, if I had x squared and y cubed, or x and y squared, as in the following example, this, by the way, is the arch we were dealing with at the very beginning of class, the arch between the circle of radius 1 and the circle of radius 2. What's my polar description for R?
Raised from 1 to 9, 0, and 9.
Which makes this integral 3r cosine theta plus 4r squared sine squared theta, all in parentheses, r dr d theta. The r is on the inside, so 1 to 2. D theta is on the outside, 0 to pi. I can't factor the r out completely because there'll be an r squared here and an r cubed here when I multiply the other one in. That means that I can't take it apart with the corollary like I did in the previous one. But I'm going to do the R integral first. What's the integral of 3r squared? R cubed. Leave the cosine theta alone. What's the integral of 4r cubed? And I leave the sine squared theta alone. That gets evaluated from r equals 1 to r equals 2. So you got to put in 1, you got to put in 2, and do the subtractions. Well, 2 cubed is 8, 1 cubed is 1, so that's 7 cosine theta. 2 to the 4th is 16, minus 1 to the 4th, that's 15 sine squared theta, and I'm integrating that d theta. Here's where I need to go back to chapter 7, because I have an integral with a sine squared in it, and that means I need the square reducing formula, which of course we memorized so thoroughly, right? Me either. What I do remember is that it comes from the double angle formula. So I remember to get that formula, I need the cosine of 2 theta formula. So I say to myself, cosine of 2 theta is cosine squared theta minus sine squared theta. And since I want sine squareds, I'm going to replace this 1 minus sine squared minus another sine squared. So that's 1 minus 2 sine squared theta is cosine 2 theta. And now I'm going to rearrange that to get the sine squared part all alone. And I get sine squared theta is 1 minus cosine 2 theta all over 2. The integral of cosine theta is easy, but the integral of sine squared theta requires me to use this, and then I'll need to use substitution. Chapter 7, section 2. Questions on the double angle formula? And that it's been a long time, right?
Is that on the formula sheet?
It's not on the formula sheet we already have, but it could very well be on your card. Shall we keep going with the integral? Okay. So this becomes the integral from 0 to pi, 7 cosine theta plus 15 over 2, 1 minus cosine 2 theta. I'm integrating with respect to theta. What's the integral cosine of theta? So this is 7 sine theta, 15 over 2, the integral of 1, the integral of cosine 2 theta. I need a u sub to do that. Do I have a 2 outside this to make it 2 d theta? There's no 2 on the outside of this cosine, right? So I'm going to get a 1/2. Oh, and at the end, that's all evaluated from 0 to pi. Yes, sir.
This is you saw by hand.
Absolutely. No, it's you're out of practice. I understand. It takes a while to get back into the swing of these, doing them that fast and that quickly. Cosine of 2 theta d theta, u equals 2 theta, du equals 2 d theta. I don't have a 2. 1/2 u is d theta. So this becomes the integral of cosine of u du with a 1/2 out in front. 1/2 sine u. So that's 1/2 sine 2 theta. You're welcome. But now I have to evaluate all of that at pi. I put a big star here, and I'll jump down to that big star here. So I get 7 sine of pi plus 15 over 2 times pi minus 1/2 sine of 2 pi minus, and then I put in a 0. 7 sine 0 plus 15 over 2, 0 minus 1/2 sine 0. What's sine of pi? What's sine of 2 pi? What's sine of 0? This is 0, this is 0, this is 0, this is 0, this is 0. The only thing that survives is 15 pi over 2. Now, the fact that this was a different function, 4x plus 3y squared, sorry, 3x plus 4y squared. I'm not exactly sure how that looks, but 3x plus 4y squared is some sort of parabolic thing, right? Parabolic in one direction, linear in the other. We want the volume under it. That's what I got. Question. What if I don't have a rectangle? A polar rectangle. What if I don't have any one? What if I have a different thing? Okay, wait a second. Graph that. It's a 4-leaf flower and it's off the axis. It's at an angle of 45 degrees, right? Remember to switch modes to polar, and then you can graph exactly in that variable. It's kind of hard to see. I'll zoom in. There it is. My little flower. I'd like the area inside one of those petals. Mia, you're looking at me like I just did something that's just maybe a space alien. Oh, okay. There, now it looks more appropriately angled. I squared it up. It's a shame we're a week late. We'd done this last Monday, it would have been St. Patrick's Day. What's the area inside this clover? Let me make my life easy. If I just find the area inside this one, I can then multiply by 4. But this is clearly not just a rectangle because its outer boundary, I think of the fan, right? The fan should start at the origin and go out until we hit the curve. That's not just a number. So a type 1 region in polar, they don't call it that in the book, would make sense if I had a boundary in R that was a function, a boundary of R that was a function. And then boundaries in theta that were numbers. The textbook uses alpha and beta for numbers for the angle rather than A and B, because A and B they think of radii, because R is in Roman and theta is in Greek. This is still doable by Fubini. I just have the theta on the inside, the R part, the functions of theta on the inside integral, and then the theta on the outside integral. Now, I asked for the area. We had a definition that said in the recording that I made before we left for break. The double integral to get the area is given by the double integral of what function? We might actually have done this on Monday. I don't remember. It's the same every time. To find the area, take the double integral of 1. Whether you're in X and Y or in R and theta, because then the volume of a slab will be base area times height. If the height is 1, then the numbers are the same. So I need the description for the region here. If this one petal is my region, R, how can I describe that with my little fan? If I'm going to just find the area inside this one petal, what are the limits of my integral? How can I describe that with my little fan? You know, we go out and then we go from one angle to the other. What's my in and out? I'll blow it up so we can see it better. For the angle? I hope so. Let's check. I know that sine of 0 is 0. And I know sine of 2 times pi over 2, that would be sine of pi. That would also be 0. So it makes sense to go from 0 to pi over 2. We can also check here by hitting the trace button and noticing that when we get to exactly pi over 2, we've come back to the origin the first time. Problem is that somebody actually once asked if 0 and pi would work, but that actually covers 2 leaves instead of 1. So you need to make sure you make the shortest trip. Okay, so I know I'm going from here with my angle, the x-axis, to here. That's the angle part. What are the radii of that fan? Well, as we spread out, we're going to see where we hit the curve. Right? So our fan is going from the origin out to the curve itself. So that makes my iterated integral, the integral from 0 to pi over 2, the integral from 0 to sine 2 theta of 1 r dr d theta. And when you integrate in r, you're going to have to plug in the function of theta. Just like on Friday, when we integrated in y, we had to plug in the function of x. Sorry. What's that mean? When I do this integral, what do I get? What's the integral of 1 r dr? Aha! But that means it's r squared on 2 evaluated from 0 to sine of 2 theta. And then that whole thing still has the theta integral outside it, right? So when I do this evaluation, I get 1/2 sine squared 2 theta d theta. And I'm back in the same boat we just were about needing that same trig formula, because I have a sine squared. Well, crud. But because I have that sine squared, I can use the formula we were just working with. So I'm not going to finish this integral because I want to point you at one more picture. We can use these. This is the volume of a slab. That's why it matches the area. Page 1014, example 4. I want to find the area under the paraboloid inside this cylinder. So imagine you have this cylinder and you cut at an angle, scraping along that paraboloid right there. Well, that would be the area under this surface above this circle. That circle is undoubtedly going to be easier to write in polar than it is in Cartesian, because that's the circle in polar. I mean, that's the Cartesian equation. That's disgusting. But if I rearrange, I get a really nice polar description for that circle. And that makes this integral much easier to do in polar coordinates than it would be in Cartesian coordinates. And the height is given by the height of the parabola. The paraboloid is x squared plus y squared. So this turns into a much easier integral. And notice, I still need the integral of a cosine to a high power, means I need to reduce that using that double angle formula twice. Because it's to the 4th power, it gets squared and then squared again. So we get cosine squared of 2 theta, which is why I end up with a cosine of 4 theta here. That pair of square reducing formulas should absolutely go on your index card. I don't want you to try and memorize them. It's a pain in the ass. I have to rederive them every time. Write them down. But I can use this idea to calculate volumes. Questions? Wednesday is question and answer. I will see you all then. I will give you your exams back then. If you have any questions, come by me tomorrow. I am going to have to cut short my office hours a little bit today and a little bit tomorrow because of 2 different Zoom meetings I've got to attend. So if you have particular questions that you absolutely want answered, email them or bring them on Wednesday and we'll talk about them. I will see you all then.